Everybody to third and the last day of the conference. Before we start, I have an announcement to make. They're going to make the group photo after the first talk. So please stay, and I guess you're supposed to open your camera to take the picture. So that's it. And the first speaker of today is Thomas Lam from the University of Michigan. And he's going to talk about Positroids and symmetric functions. Please welcome the speaker.
Thank you. Thank you for the introduction, and thank you to the organizers for inviting me to speak. So I'll be talking about joint work with Pasha Galashian, which is about some symmetric functions that appear in the theory of positroids. So I'm just going to I'm going to start by quickly saying sort of what a positroid is, the combinatorial data that goes into a positroid. So the setting is as follows. You give me a k by n matrix. So this is a k by n matrix, and I'll assume the matrix is full rank. And then the columns of the matrix are labeled are called V1, V2 up to Vn, and they're labeled cyclically. So I have Vi, I is an integer. And I'm going to define a function from integers to integers, and the function f of v depends on v. V is, right, so V is this matrix. So you give me a k by n matrix V, and I'm going to define a function, and the function is given by this formula. So you ask what's the smallest value of j such that Vi belongs in the span of the next few vectors. Vi plus 1, Vi plus 2 up to Vj. So you find j the smallest such that Vi belongs in the span of the. So let me just do this example down here with this 2 by 5 matrix. So in this case, k is equal to 2 and is equal to 5. So V1 is this vector, V2 is this vector, and so on. So what is f of 1? F of 1 is equal to 2 because V1 is in the span of V2, because these two vectors are parallel. So what about f of 2? F of 2, it's not equal to 3 because V2 and V3 are not parallel. F of 2 is not equal to 4 because the span of these two vectors, I mean, this vector is the 0 vector, so it doesn't increase the span. So we're still doesn't include this in the span. So f of 2 turns out to be 5. F of 3, so V4 is the 0 vector, so that doesn't help. V5 is not parallel to V3, but V3 belongs to the span of V5 and V1. So f of 3 is equal to 6. And you keep going. So f of 4, so 4 is the 0 vector. So f of 4 is just equal to 4. So it's in the span of no vectors. And f of 5 is in the span of everything. It's 8. So you need to take f of 5 is in the span of these 3 vectors. Okay. So so the proposition is just a linear algebra fact, and this is what this is the basic thing that I'll call a positroid. Is that you give me any k by n matrix and you do this game and you'll get this. And this is repeated periodically because because of this assumption, the periodicity assumption, this function will be periodic. And it turns out that it always defines a bijection from integers to integers. So that's not completely obvious, but it's not difficult to prove. It's just a linear algebra thing. So it's periodic, that's by definition. It's bounded, so f of I is between I and I plus n, just because you're always in the span of yourself. So you can't wrap around that many times. If you wrap around n, you come back to yourself and you'll always be in the span of a collection of vectors that includes the same vector. And then the last one is a little bit tricky, is that sort of the average increase is k. That's what this last one says, and that is not so obvious, but is again just linear algebra. Okay, so such things, such bijections from the integers to integers, I'll call a banded affine permutation. And so this is the main. So when I say positroid, I'll basically mean one of these things, a kind of affine permutation. And associated to such an F, so F is a banded affine permutation, there's two subvarieties of the Grassmannian that are potentially of interest. One's the open positroid variety, another one is the closed positroid variety. And so the open positroid variety is you take all k by n matrices whose F is equal to a particular F. So I think of the Grassmannian as the collection of full rank k by n matrices, modulo row operations, etc. So if you give me a point in the Grassmannian, I ask what is its F, what is its F, and I just take all the points with the same F. And that's the open positroid variety. It turns out that this guy is a smooth, irreducible subvariety of the Grassmannian. It's not closed though, and it's only locally closed. And if you take its closure, then you get the positroid variety. So I won't say that much about these things, but the point is that if you give me one of these things, so something that satisfies this collection of conditions, I can produce for you a subvariety of the Grassmannian. So there's some geometry associated to every banded affine permutation. And these positroid varieties, I guess they first came up in total positivity and also separately in Poisson geometry. Since then, they've been a lot of fun to think about in Schubert calculus, and they've had sort of really striking applications in particle physics in the theory of scattering amplitudes. But today I want to talk about positroid varieties and symmetric functions. And first, let me mention sort of what this talk is not about is a theorem I proved with Knudsen and Steyer. I think this is nearly 10 years ago, which is that if you the cohomology ring of the Grassmannian is basically a quotient of the ring of symmetric functions, which quotient it is depends on k and n, so the size of the matrix that you're looking at, and it's a very standard fact in symmetric function theory that if you look at Schubert varieties, which are some special cases of positroid varieties, so these varieties include Schubert varieties as special cases. If you take the Schubert varieties, you get the Schur function, and it's a natural question, what happens if you take any positroid variety? And the answer is you get something called an affine Stanley symmetric function. So I won't define this thing. So this is, but this is this is going to be a Schur positive polynomial. It's positive in Schur polynomials inside this ring. This is the kind of function you get. So this is something that if you look at the class of a positroid variety, you get this affine Stanley. So this is an old theorem, but recently with Galashian, we found a sort of a different way to see sort of symmetric function combinatorics coming out of a positroid, and it's in sort of a different way. And I'm going to state this theorem just for a special case. What I'm going to do is I'm going to take this particular banded affine permutation. So this is a bijection from integers to integers, and it's the sort of one of the easiest bijections. It just adds k. So if the input is I, the output is I plus k. So that is a particular banded affine permutation. It corresponds to a positroid variety. It turns out this positroid variety is it's called the top positroid cell. This is some dense open subset in the Grassmannian. So let's write it down. So this thing belongs to the Grassmannian, and it's dense and open. So if some open subset is a manifold inside the Grassmannian. And what Galashian and I looked at was what's the topology of this subvariety. So this is a different question to the above. So here we're looking at some subvariety of the Grassmannian, asking what its cohomology class is, which will belong to the cohomology ring of the Grassmannian. Here, I sort of forget that it's sitting inside the Grassmannian. So I ignore that it's sitting inside the Grassmannian. I just have this space and I ask what is its topology. And it turns out that we get basically the two different Q Catalan numbers by doing two different very obvious things. One is I just want to count the number of points in the positroid top cell. And it ends up that we basically get a Q Catalan number, the algebraic Q Catalan number, up to some simple factor. And this result requires the condition on a GCD condition on K and N. So there's a variant of this result for which we'll talk a little bit more about. So one thing is to count the number of points over a finite field using the fact that these this procedure here where I define this bounded affine permutation, this makes sense. I didn't say what kind of entries my matrix has. So this matrix could have entries in complex numbers or in real numbers, but also over a finite. So any field, you can still do this game. So it doesn't really matter. Anyway, so these varieties here are defined over any field, in particular defined over a finite field, and I can count the number of points over a finite field. So that's one thing that you can do, and you end up with a polynomial in Q, and it's this, it turns out to be this polynomial. Another thing you can do, which is the topology question, is you just take the complex variety and you look at its cohomology groups. And then you can take its Poincare polynomial, and again, you get something, and you get the other Q Catalan number, which is the sum over D here is sum over rational dict paths. So this D is so you get the another Q analog of the rational Catalan number, and that's the Poincare polynomial. And you can sort of combine these two results to get a sort of more powerful result that there's a QT version of this, which is I won't say what it is. So there's another invariant of this variety called the mixed Hodge polynomial, and the mixed Hodge polynomial recovers the QT rational Catalan numbers. Okay, so these are rather these two theorems. So first, what is the cohomology class of the variety, a closed variety, and what is the topology of this open variety? They're sort of different questions, but they're based upon just this combinatorics. I mean, what's the input data? The input data is just one of these Fs. You give me a bounded affine permutation, and in this first case, you'll get this affine standing symmetric function. And in the second case, I only told you what for this special F, what you get, but you get some kind of Catalan combinatorics. And actually what this talk is really about is what happens if you take other Fs. So here I took this F, which is this, the simplest bounded affine permutation, sometimes called the identity. It's not really identity, but it's the shift permutation. And we get this Catalan combinatorics. So what happens when you try to do other Fs? What kind of combinatorics do you get in the second theorem? Let me mention that this question of what's the relation between these two theorems, and I haven't figured this out yet. I don't know. These are two different questions which have sort of a lot of structure in symmetric function theory, but I don't really know how to relate these two theorems yet. And basically what I want to talk about is to focus on the second theorem, so this recent theorem, and try to put it in the context of some questions that are sort of modern interest in symmetric function theory. So I think this is of interest to this audience. Okay. So to formulate the kind of expectation of answer, so this is work in progress, and quite a bit of it is conjectural. So to formulate the kind of answer I expect, I want to introduce some symmetric function operators. So these are operators of symmetric functions called elliptic Hall algebra operators. So the elliptic Hall algebra initially studied by Berman and Schiffman, and sort of the action on symmetric functions described in Schiffman and Vassereau, and studied also by Negut in the context of something called the shuffle algebra. I'm going to give definitions. I'm going to give definitions following a paper of Bergeron, Garcia, Levin, and Shin. So the elliptic Hall algebra is generated by some operators called Q sub A comma B. And so I'm going to define these operators. So first of all, the elliptic-hole algebra is defined as an algebra, a non-commutative algebra by generators and relations. And separately, it has an action on symmetric functions. And I'm going to define only the action on symmetric functions for you. I'm not going to give the sort of abstract definition of elliptic-hole algebra. I'm going to define this algebra as an algebra of operators and symmetric functions. This is not how it was originally defined. Anyway, okay, so first I'll define some operators called d sub k, where k is a non-negative integer. And it's defined using this by taking a generating function over k, which is that d sub k acting on a symmetric function f you take a plethysm of this kind of to me, sort of originally somewhat unusual plethysm, x plus m over z. Z is a parameter that's keeping track of the k variable, and m is this particular polynomial in Q and T, 1 minus t times 1 minus q. And then you do some kind of vertex operator kind of style generating function acting with the elementary symmetric functions, and the coefficient of z to the k is the operator d to the k, d sub k. And this formula defines d sub k for every k greater than or equal to 0. So if you haven't seen this before, this is somewhat mysterious, and I won't be shedding that much light on this formula right now. So I'm just going to be telling you what the definitions are. What are the Q operators? So by definition, Q1 comma k is d sub k. Q0 comma k is sort of easier. It's basically a normalization of sort of, I think of as a somewhat easier plethysm of the homogeneous symmetric functions. Those are the Q's. So I guess we should just think of Q0k as basically homogeneous symmetric functions, Q1k as this unusual-ish symmetric function operator. And then the other operator is Q sub a comma b. So this defines it. If the first index is 1, then it's this operator. If the first index is 0, it's just multiplication by a homogeneous symmetric function. What happens if the first index is not 0 or 1? Then it's defined in this recursive manner, and it's a theorem that this recursion gives a well-defined collection of operators. So what you do is, if you want to know, I'm just going to do it by example. So if you want to know what Q23 is, then you take a 2 by 3 rectangle, as I've drawn here, and you find the I feel like this is a little bit not aligned. Let me see if I can move it. Okay, that looks slightly better. Okay, so I draw a 2 by 3 rectangle, and I draw the main diagonal, and I take the lattice point that's below this main diagonal that's closest to the main diagonal. Maybe I should zoom in here. Okay, so I draw this main diagonal. I take the lattice point that's closest, and there's a more precise way of saying it, but I think at least in this case, it's clear that this lattice point is the closest to the main diagonal here. And then Q23 is given by the commutator of 2 other operators, which are kind of smaller. It's given by the commutator of this, so this Q sub this vector and Q sub this vector. And there's a 1 over m, so some scalar in front. If I want to do Q35, again, I draw and let me move this. Okay, that looks slightly better, but not super good. Okay, so my rectangle is not so, the sides aren't so parallel, so there's a little bit. So now I draw the main diagonal, which is in a 3-5 rectangle, and I find the lattice point, in this case, this point. This lattice point is the closest to the main diagonal and below, and then I'll take these 2 vectors here, and that will give me the 2 Q operators whose commutator I have to take. So that's the definition. If sometimes if you take Q sub AB and Q sub AB, it's they have a common factor, in this case Q sub 12,8, and here I drew a picture of Q sub of 12,8, and you see that actually there are many lattice points which are very close to the diagonal. Actually, they're sort of equally close to the diagonal. There's a bunch of lattice points equally close to diagonal. Part of the theorem is you can take any one of those. So I chose this one, and this is true, but if I picked another one, I would get another true formula for Q sub 12,8. And this defines Q sub AB for A and B, certainly both positive integers. If you repeat this procedure, and the theorem is that it's well defined. Okay, check. Any questions? Okay, so to summarize, elliptic whole algebra operators are basically generated by these kinds of operators, which is a sort of, I don't know, vertex operator slash trapezoid kind of operation. Together with a lot of commutators will give you these elliptic whole algebra operators. A particular special case of this operator is probably pretty familiar, is that the operator, the symmetric function operator that's Q sub n plus 1 comma n, if you act on plus or minus 1, you get nabla of En, which is the subject of the shuffle theorem. And yeah, and I think the audience knows about the shuffle theorems and shuffle conjectures very well, probably better than myself. There's so the rational shuffle theorem is a formula basically of these operators acting on plus or minus 1. So there's some sign convention here. So if you take Q sub Mn and Mn are relatively prime, then there's some formula for the symmetric function you get when you take this operator and act on 1. And I won't spell out the details on the right hand side here. So there's some formula, and it's a sum over parking functions, and you end up with a with certain area and dim statistics, and you get a symmetric function. And this is the result of Mallet. The rational version of the shuffle theorem is conjecture of Gorski and Legut. I need a slide to define the collection of symmetric functions that's sort of interesting for positroids. I need a slight variant of this, which is when M and N are not relatively prime, it turns out that basically this elliptic whole algebra is a huge collection of operators, and it's graded by M and N. And when M and N are not relatively prime, there's sort of a lot of good choices for some kind of basis element in that subspace. QMN is one of them, but there are other interesting ones. And here's how to set it up formally. I'm only going to do a sort of a special case of this. So what I want to do is to define some operators that I'm going to call E sub AB. And the notation here, when I write it like this, is M and N are relatively prime, and K is the common factor. So here. So in this definition, GC of Mn is equal to 1. So what I'm doing is I'm defining some elements in the elliptic whole algebra whose indices are labeled by things whose common factor is K. So K is the common factor. And the way, so if K is the common factor, what I do is I take EK and express it in terms of these Q operators. So remember, the Qs are basically plathistic substitutions of homogeneous symmetric functions, and I ask what the coefficients are. And I use the same coefficients, but instead of putting Q0 lambda I put this thing here, Q sub M lambda I and lambda I. And I do the same thing for H, and I'll get some H sub ABs. So So this is so this definition is just defining. So let me just write down what this definition is supposed to do. Is I'm defining some elements of the EHA called E sub A B and H sub A B, and they belong to they still belong to this thing called elliptic Hall algebra. There's some linear combinations of these elliptic Hall algebra symmetric function operators, but they're not exactly the QAB. So the point is the QABs are a little bit like power sums. Actually, these QABs are a little bit power sums and a little bit like power sums, and there are some things that are more like elementary and homogeneous symmetric functions. So this definition is in the same paper by this BGLX. Let me write this down. So this way of defining these operators is okay. So and BGLX they use this Bergeron, Garcia, Levin, and Shin. They use this formalism to define KMKN shuffle theorem. So a shuffle theorem, a rational shuffle theorem where they don't have to have GCD equals to 1. In fact, they defined it. So they did much more than this. There was a compositional version of the shuffle theorem and so on. And again, it was proved by Mallet, and their conjecture and now theorem tells you what EMN does. But now I should really write EAB. So there's some positive formula for EAB. Okay. Yeah, so A, B are no longer co-prime. So it turns out that the operators that come up naturally in studying positroid, the cohomology of positroid varieties aren't the E's, but the H's. So the E's are the ones that naturally extend the shuffle theorem from the rational case to the, for the GCD equals 1 rational shuffle theorem to the general shuffle theorem. The H's turn out to be the ones that that come up when we did calculations with positroid varieties. So that's what I'll focus on now. So let me just give a sort of high level abstract version before I give the precise version. The conjecture that we have is for a large class of positroids, which I'll tell you about in a moment, there's a topological invariant of the positroid variety, which is, there's a lot of jargon here, but this is a topological invariant on the left-hand side is compactly supported torus equivariant cohomology. Is isomorphic to some piece, and isomorphic here I mean in terms of generating functions, isomorphic to some piece of the of a particular element in the elliptic Hall algebra that depends on F, acting on 1, and I take a particular coefficient that's familiar to many people, which is the Catalan coefficient of the symmetric function. So this Q sub, so F is one of these bounded affine permutations. So bijection from integers to integers, periodic, bounded, blah, blah, blah. I'm going to tell you Q sub F, which is some element in the EHA. And this, it'll really be described in terms of these H operators. And I act on 1 and I'll get a symmetric function. And then I take a particular Schur function coefficient of it. And that will be the sort of Catalan object. And the Catalan object will correspond to this, well, that will be the generating function of equivariant cohomology. Okay, so what is this? So we don't have this conjecture for every single bounded affine permutation, but for some class of them. And so I say a large class. So the large class of positroids in the conjecture is a class that's called repetition 3. This is defined in a paper last year that I wrote with Galatian. But for this talk, I'm going to talk about an easier class of positroids called concave positroids, which is easier for me to give the definition and easier for me to describe the operator Q. So to give the definition, I have to introduce some knots and links associated to a positroid. And 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 I'm going to do it by example. So remember that F is a bounded affine permutation. That's bijection from integers to integers. And in this case, I'm going to take n equals 8. Here n is equal to 8. So F is 8 periodic. So if I just take a window, I ask what f of 1 is. So here f of 1 is 4, f of 2 is 6, f of 3 is 8, and so on. So all the information is captured in this part of it because it's periodic bijection. What I'm going to do is I'm going to draw in this little square with identified sides, which I think of as a torus. So I'm going to identify this side with this side and this side with this side. So in this torus, along the diagonal, I'm going to write the numbers 1 up to 8, so that's 1 up to n. And then I'm going to take these numbers here, think of it as just a usual permutation, and draw the corresponding dots here. I'm going to assume that there are no fixed points, and I've drawn the dots in this way. Right. So one goes to 4 is this dot here says 1 goes to 4, 2 goes to 6 is this dot, and so on. And then what I do is I draw some strands, and these will be strands of a link that is going to be a link on a torus. The strands, what I do is I draw from each diagonal element, I draw a strand up to the dot in the same column, and then I draw, and from the dot in the same column, I'm going to go right and then wrap around, and then you see that 1 goes to 4. So this is what I've done here. So 1 goes to 4, and then 2 goes up to this dot, and then it wraps around and it goes to 6. And then 6 goes to 1, 2, 3, 4, 5, 6. So 6 is supposed to go to 11, but 11 is free. So 6 goes all the way up to here, and it goes to 3. Okay. And the other rule is how do you know which strand goes over another strand? So there are going to be some crossings, and you have to describe a knot, you have to say whether the strand is an overcrossing or an undercrossing. And to decide, one rule that you can use is that the high target is over low target. So for example, 1 goes to 4, the target is 4, while this one this one is 8 goes to 7, the target is 7. So the target is 7, so it goes over this strand. Over here is this picture where I've sort of I've smoothed out all the strands here. And now I have this link, and this is a link which is I denote L sub f. So if you give me a bounded affine permutation, I have this link, which is a link drawn on a torus called L sub f. Okay, so this works for any positroid, and I'm going to tell you a subclass of positroids called concave positroids, where this link has some special extra bonus properties. And let me show you a picture of it. So the kind of link that I'm interested in is the kind of positroid I'm interested in are positroids that come up in the following way. So we're going to draw a k by n minus k rectangle here. This is a k by n minus k rectangle, and I'm going to draw a curve from one lattice point to the other lattice point. And this curve will be, I'll ask for it to be concave. So any secant on the curve is below the curve. And so I call that C. And then you can take the, so this is a k by n minus k rectangle. What I'm going to think of it is that the unit square is a fundamental domain for the torus. So every copy of the square is one copy of this square here. And what I've done here is I've intersected the curve with the diagonal in every unit square and marked the positions. The positions are marked so that the number is high if you're close to this side, and the number is low if you're on this side. Okay, And then I take this whole thing and I project it to one of these squares. So I take this whole curve and I project it and it looks like this. So this, for example, this part here is this part. Okay. So this whole strand projects here, and you're going to see many strands, and the number of strands you see here in this picture is just the number of squares that this curve passes through. And then you can ask whether this picture is isotopic to a picture that you get from a positroid. And in this case, yes, it is. It's isotopic to the positroid where 1 goes to 6, 6 goes to 4, 4 goes to 9, and so on. So this is this positroid, which is specified by the labels here, comes from a concave curve, and so this is one of these concave positroids. And so the conjecture is that for every concave positroid, I can give you an element of the EHA, an element of the EHA, such that the topological invariant of the positroid is calculated by the symmetric function. Okay, so there are some special cases, some of which we sort of, if the concave curve that you start with, if the concave curve is just a straight line between the two endpoints of a rectangle, so that k and n minus k are relatively prime. So this case is the case where the corresponding positroid length is a torus knot. So this is L sub f in this column of L sub f. So if f comes from this curve, then L sub f is something called a torus knot. And in this case, the corresponding operator is just Q sub. I don't know why I wrote 4-3, 5-7. If I did my, sorry, 7-5. So the corresponding operator is Q sub 7-5, which is actually H sub 7-5 because 7 and 5 are relatively prime. If you take a rectangle and it, so k and n minus k are not relatively prime, and you draw the main diagonal, this is also a concave curve, but it now passes through a lattice point. And then the corresponding L sub f is a torus length, and the operator that you want to take is basically a power of one of these torus knot operators. So you take you divide by the common factor. The common factor between 4 and 6 is 2. So then after you divide by common factor, you get 3,2, and then you square. If you take a concave curve, so again, basically in the same case, if you take a concave curve that is such that it just barely misses the lattice point that it could have passed through. So the main diagonal passes through a lattice point. If you take a concave curve that goes above that lattice point, but otherwise is exactly as close to the diagonal as possible. So here's a concave curve, and it just goes above this lattice point, but otherwise it's the same. Then you get this H operator. So that's what I mean when I said the H operators turn out to be the operators that are natural for positroids. These H operators defined using this really, I mean, if you haven't seen these things before, you're not going to be able to you're not going to be able to gather much of the, I mean, there's very little intuition you can immediately get from this formula. But anyway, this well-defined some operator, and these are the ones that come up by these positroid knots. So this turns out to be a knot, not a link. So it's only got one component when it just misses that lattice point. If you have a concave curve that is sort of very close to a diagonal, but has multiple pieces that are sort of as close to diagonal as possible, then you just multiply the corresponding operator. So in this case, there's a 6x4, a 6x4 rectangle where you have this, where the picture looks like this, and then another piece which is a 5x2 rectangle where you just go straight, and it's still concave. This whole curve, the whole thing is concave from this corner to this corner. Then you just take the product of these two HA operators, and this is going to be a positroid length. Now, if you give me a concave curve that is further from the diagonal, then there isn't it's not going to be just the product of these H's. The conjecture is that it's going to be given by recursion. And here I'm going to tell you this formula for this recursion. So the recursion relates the EHA operators coming from concave curves that differ by a lattice point. So here's a concave curve going from here to here. Here's another concave curve going from here to here. The only difference is that this concave curve, in terms of lattice points, the only difference is that this lattice point is above the curve and this lattice point is below. And the two are related by this formula. This one is equal to QT times this one where it's below. And then there's a correction factor where you pass through the lattice point. And remember, when you pass through a lattice point, then you just multiply operators. So let me write that down here. So when you pass through a lattice point, in some sense, is it's a smaller value of K and N. Because you then have to separately figure out what is the operator for this part and what is the operator for this part, and you just compose these operators. So yeah, okay. So just to give you some examples, I took these operators. I took these concave curves. So this one is Q43. As I said before, this is 4 and 3 are relatively prime. So this is Q43, and you get this formula. If you do the same thing for this thing, which is now it no longer goes straight across, but it went above this lattice point, then you get this formula. And now if you also go above this additional lattice point, then you'll get this formula. So these are different for the same K and N minus K are 3 and 4. They are different concave curves, and they give you these different operators, and I calculated them, and I got these are Schur functions. So these are the Schur function coefficients of these operators you get. So these operators you get by applying this recursion. Also, I should say that when you write an element of the EHA, because the EHA has all these relations, so it has all these relations up here. I mean, back up here, there are these relations, like 2, 2, 3 is equal to these things, but this guy is equal to many different possible expressions. So there are lots of relations between the operators. It's not so clear. Sort of what whether there's a canonical way to write this in terms of the Qs and so on. So that's why I'm labeling instead of telling you what the EHA operator is in terms of the H's, which is some linear sort of alternating sum, I'm telling you what it is just by drawing this concave curve. Because I'm not confident that I have the best way of expressing it in terms of the H's. Okay. So part of the conjecture is that for this same class of concave curves, these EHA operators produce Schur positive symmetric functions. So actually, the conjecture is for repetition free, and I'm not talking about that today, but for this class that I talked about for concave curves, for each concave curve I produced for you using this recursion, an operator in the EHA, and we conjecture that it's a Schur positive operator. And it is related to some other work on knots that have basically on knot homologies that have knots whose knot homology have even cohomology. They're studied by Oblomov and Rosansky. It's also related to some conjectures of Glacier, Kamen, Morse, Pun, and Seelinger, and Negut as well. So which cases have been studied? So the case where basically everything is known is the case where you just take the concave curve you just take this case, which is just Q75. So that's the case of a torus knot. And we know, due to the work of Mallet, we know the combinatorics very well. And we know its relation to positroid varieties via my work with Galashin. So the combinatorics of the operator studied by many people, but most notably at the end by Mallet, and the connection to positroid varieties is my work with Galashin. And even in the torus link case, it seems like not everything is known. So this is the case where you draw the main diagonal that passes through a lattice point, and then the corresponding topological object, the corresponding thing in knot theory is a torus link. So it's a knot that has multiple, it has multiple components. And already it doesn't seem that we completely understand the this symmetric function operator, but there's some recent conjectures of Andrew Wilson about this. Earlier, we studied something that we called Catalan numbers for positroid knots. And what we showed is that if you give me one of these concave curves, then you can define this Catalan number associated to it, which we can define by taking this torus equivariant cohomology and taking the Euler characteristic of it. And this is the thing that should correspond to of a particular Schur function coefficient. So part of the conjecture here is that this should be, the Schur function coefficient should be the Catalan number corresponding, or Qt Catalan number corresponding to corresponding to that positroid variety, corresponding to that F. And in that case, we proved that the Catalan numbers have the predicted, have the correct use the correct number if you forget Q and T, is that it's the Catalan number is the number of Young diagrams that are sort of strictly above the curve. Equivalently, is the number of lattice paths that stay strictly above the curve. Okay, so I'm nearly out of time, but let me mention that the part of the conjecture that we can prove is the specialization at T is equal to 1 over Q. This specialization, T is equal to 1 over Q, well, it's well known in sort of McDonald theory, Qt Catalan theory, that this is an interesting specialization with lots of special combinatorics. This, in terms of geometry, that corresponds to the point count. And somehow the point count has the feature that you can, if I'm trying to calculate the point count of a variety, I can just cut it up into pieces and add up the answers, and there's no long exact sequences. So that simplifies all the calculations. And let me just explain really quickly, sort of in the last 2 minutes, sort of the basic ingredient in understanding the T equals 1 over Q specialization of these conjectures, and uses something called skein theory. Skein theory is we take a surface S, and we just take we just define an algebra by taking all possible links that you can draw on the surface. And these links that you draw on the surface, they're going to have some crossings. And whenever you see 3 links and they're locally only differ in the following way. So one of them has an overcrossing, one of them has an undercrossing, and one of them has no crossing. Then the corresponding links are declared to satisfy this equation in the skein algebra. So you take the sort of 3 abelian group spanned by all links that you can draw on the surface up to isotopy, and then you mod out by these skein relations. And then you make it into, so this defines some module, but you make it into an algebra by saying, if you want to multiply 2 links, I draw a link and then I just draw the other link on top. I just draw it over such that every strand of my second link is going to be an over every strand of the first link. So this gives me a skein algebra, and a basic theorem of Turayev is that if you choose the surface to be an annulus, to be a cylinder. So if you take your surface to a cylinder, you ask what are the links that you can draw on the cylinder, modulo the skein relation, then you just essentially get symmetric functions. So there's a plus here, which I won't explain, but you essentially get symmetric functions tensored with Q. So there's a Q in the skein relation, and it's the same Q here. And then if you take the surface to be a torus, there's a theorem of Morton and Samuelson which says that the skein algebra of the torus is isomorphic to the EHA evaluated at t equals 1 over q. So this special value t is equal to 1 over q, where we can sort of where we feel sort of confident about this all these ideas is the case of that happens in the Morton-Samuelson theorem, and up to a lot of normalizations, which are actually kind of technical. Roughly speaking, if you take the knot, that is the TAB knot, it goes to this operator QAB inside the EHA. So there's this isomorphism between the skein theory of the torus, skein algebra of torus, and the EHA at some evaluated at some parameters. On here, you can draw any knot you like. You can draw this thing called the torus knot. Here's an example of a torus knot, T32. You draw the torus knot, then that gets mapped to the operator Q32. Except that there are lots of normalizations on both sides, and this is not literally correct. I think I'll stop here, but I'm saying, but the so this t equals 1 over q specialization is particularly easier to approach because you have a skein algebra description, and there's further progress on this direction, but I don't think as of yet it's completely, I mean, Morton and Samuelson have a further result that relates the whole EHA to the skein of a torus with a puncture in it, but it's a little bit more complicated, and it's not, and there's a collection of conjectures, so it's not completely proven yet. But at this specialization, we understand the skein of the torus, and as I said before, every time you give me a positroid, I can give you a torus link. So if you give me a positroid, I can give you a link in the torus, and so this link in the torus gives me an element in this skein of the torus. So naturally, if you give me a positroid, I can give you a link, which gives me an element in here, which then gives me an element in the EHA. And so this is where our conjecture comes from. Okay. Stop here. Thank you.
Okay, let's thank the speaker. Are there any questions?
So I have one. Really nice talk, Thomas.
Thank you.
What goes into computing the cohomology of these open positroid varieties? Like, I saw some kind of a nice factorization on your second slide or something. I mean, is there some kind of fiber bundle or?
Actually, that's difficult on both sides, let me say. Right, so first of all, in this case, in either of this case or this case, there's a factorization of the operator. No, it's not a fiber bundle, and we don't know easily from the positroid side why something like this would be true. So that's a mystery to us. The way we do is we connect it to, we have a theorem that connects the cohomology to a link homology group. And this works in a very general setting. The other thing that's difficult is even on the symmetric function side, it's not quite a factorization, because what you have to do is you have to take this operator and you have to act on one. And after you act on one, the first one you act on one, it is at least in spirit similar to these shuffle theorems. So you might, well, I mean, certainly if you take Q32, if you take Q32 and you act on one, then that is a shuffle, one of the shuffle theorems. But then you have to take Q32 and act on it again. And that, yeah, I don't know, I actually don't know much about exactly what is known about how to take Q32 and act on some rather complicated generating function. So it's yeah. So the second, already the second guy acting is pretty complicated, and we don't know why it is. The only reason why we decide to decompose it like this is just the combinatorics of this curve, and it is quite mysterious from both perspectives, actually.
Thank you.
Oh, I see a question in the chat. Is there a combinatorial interpretation for Hopf coefficient other than 1 to the n? So a Schroeder type, maybe. I expect that yeah, we don't know the answer to that. So back over here, I said that if I give you a concave curve, then should be the number of dig paths above the curve. And even that, we don't know the QT. We don't actually know the area and dim from such things. We didn't. Yeah, I think there should be a good answer to this question about the Hooke coefficients, but I haven't thought about it.
If you
Are
didn't
there any-
know,
Oh, okay.
you know, a
Sorry.
dim thing for the whole symmetric function, you can just specialize by plugging in like a certain kind of, what I call it the Hooke shuffle. Yeah. So, but that's assuming you knew the monomial expansion of the whole symmetric function.
Right. Yeah. Yeah. We're quite far from knowing that. Yeah. Thank you.
Hi, Thomas.
Yes.
Is there a action of the mapping class group on the skein algebra? And if there is, does it behave nicely with these positroid knots that you?
Yes, there is a mapping class group on these. I don't think it behaves nice to the things that I'm talking about. So one feature of just this EHA algebra, so this large collection of elliptic whole algebra operators, is that actually strictly speaking, elliptic whole algebra operators, it includes operators Q sub AB, where AB are integers, not just positive integers, but integers. And there's an SL2Z action on this algebra. So it's indexed by lattice points. So these operators are indexed by lattice points, and which are integer vectors in two-dimensional space. And there's an SL2 action on this coming from a torus. And the one feature is that the positivity, all these conjectures about Schrödinger positivity and so on, they seem to only come up in the positive part of the EHA, not in the negative part. So you need your A and B to be positive, and before you will get some positivity, and even more, the positivity is even stronger. So you can think of this condition that it's concave. So I said we have some conjectures for if this curve is concave. What happens if it goes like this? If the curve is like this, you can still take the two operators and compose them, and then you end up with a you end up something with Schrödinger coefficients that are not positive. So then it's some operator that turns up and what this the mapping class group actions do I think it will mess up these it will swap positive operators with non-positive operators. So I think it's rather complicated what should happen there. I don't think there's a straightforward thing to say there.
Okay, no, thank you.
Any other questions? If there is none, let's thank the speaker one more time.
Thank you.